All right, good morning, everyone. So let's get started. In the last class, I gave a proof of the converse part of the channel coding theorem. What I derived was a weak converse, wherein we showed that if you try to operate at a rate above capacity, then asymptotically the probability of error cannot be vanishing in n. It is always bounded from below by some small epsilon, which is strictly greater than 0. And I also mentioned that it is possible to prove a strong converse, but I will not be doing so in this, I will not be proving that in this particular class. The strong converse basically says that if you try to operate at any rate above capacity, then asymptotically the probability of error is in fact 1. Okay, so if you look at the variation of the asymptotic probability of error with the asymptotic rate, then there is this phase transition. So below capacity, the probability of error is really small. It's close to 0. But as soon as the rate at which you're operating is above capacity, it suddenly jumps to something close to 1. Right? So this was sort of an application of Farnose inequality and the data processing inequality, and in fact we'll be using these tools. We'll be using a very similar approach when we try to prove a converse result for or a converse for a channel coding theorem for not point-to-point channels but for multiple access channels as well. But then we'll see that as we try to derive capacity results for broadcast channels, these tools are insufficient. So we'll develop some more tools which will be used to prove converse results for broadcast channels. And one very useful tool is what is commonly known as Mrs. Gerber's lemma in the literature. And in this class, I'll derive a proof of Mrs. Gerber's lemma. So before we proceed, are there any questions from the last class?
Sir? Sir? Hello?
Hello, yes, please go ahead.
Yeah, so what I'm saying is, can you please just repeat once that Mrs. Gerber's lemma?
Yeah. So I will do the Mrs. Gerber's lemma in detail, but if there are any questions regarding the other topics covered in the last class, just let me know. Okay, so in this class we'll discuss Mrs. Gerber's lemma, and the whole point and what Mrs. Gerber's lemma says. It's a class of results wherein the goal is the following. So suppose that you know what the entropy is for the input. So suppose that you're transmitting X through a channel and you get Y. And what you want to understand is what is the entropy of Y given only the entropy of X. Okay. Suppose that you don't know what the distribution of X is, but someone just tells you that the entropy of X is some quantities, maybe 0.3, and I pass it through this particular channel and I get the output Y, and I want to know what is the entropy of Y. So for any X I want with a certain entropy, I want to know what the entropy of Y is. Now, in general, without knowing the exact distribution of X, we may not be able to say exactly what the entropy of Y will be. But can we at least get a lower bound on the entropy? And that is what Mrs. Gerber's lemma says for the very specific case of a binary symmetric channel. So given h of x, how large can h of y be? Okay, so let's do a simple exercise. In the last class, we did this simple exercise. Suppose that you have x, which is Bernoulli Q, right? So if x is Bernoulli Q, then the entropy of x is simply equal to the binary entropy of Q. And you pass it through a BSCP, then you know exactly what the entropy of y is going to be. It is going to be the binary entropy of p into 1 minus q plus q into 1 minus p. Right? And we use this special notation p star q to denote the function p into 1 minus q plus q into 1 minus p. Okay, so in this particular case, we know exactly what this is going to be. All right, and so this is pretty straightforward. But the more complicated case is when you have a random variable. What if x and y are dependent on some other random variable u? Right. So suppose that you're generating x. So you generate a u, and then you generate a random variable x, which is conditionally dependent on u, and then you pass this through a BSC, right, a BSCP, and then you observe y at the output. So in this case, suppose that I'm only telling you what h of x given u is. I don't tell you the distribution of x. I don't tell you the distribution of u. I only give you h of x given u. Then how large can h of y given u be? Can I get a bound on h of y given u? And that is precisely what Mrs. Gerber's lemma says. It says that h of y given u is always lower bounded by the binary entropy of h2 inverse of h of x given u star p. So let us compare this with the case where we just had this x being passed through a BSCP and there was no u sitting in between. Right? So in this case, we know that h of y, the entropy of y, is the binary entropy of p star q. Okay. But what is q equal to? I can write q as h2 inverse of h of x. So basically, q is just h2 inverse of h2 of q. All right. But I can write that as h2 inverse of h of x. Okay. And so this is an equality in the case of a BSCP, right? Where there is no dependence on any u. Okay, and this directly extends. So given any arbitrary u, h of y given u is always greater than or equal to h2 inverse of h of x given u star p. Okay, so for just x passed through a BSC to get y, we have h of y to be exactly equal to h2 of h2 inverse of h of x star p. Okay, and what Mrs. Gerber's lemma says is that even if x is dependent on some random variable u, then the conditional entropy of y given u is greater than or equal to h2 of h2 inverse of h of x given u star p. Okay. Any questions? Okay, so maybe to understand this better, let's look at it. Yes.
If the bound is actually greater than or equal to, then it should be how minimum, isn't it? How large?
Okay, fine. How small can it be, I suppose?
Yes.
So in some sense, okay, it is how large can it be because it's at least as large as this particular quantity, right?
Acha, okay. Okay.
So yeah, I was being loose when I said that, but what this class of inequality gives is a lower bound on h of y given u in terms of h of x given you. That is what we want to understand.
Okay. Yes.
Okay, and this is for the specific case of where you are transmitting x through a BACP. Right, so it's for a very specific channel. But this can be extended to more general additive noise channels, and we will look into that later. So uh, we will show the so-called entropy power inequality. We'll show that for continuous channels, if you have a channel y equal to x plus z, then where x is a continuous random variable and z is a continuous random variable, then you have the following inequality for h of y. So y is the output of the additive noise channel, x is the input to the channel, and z is the noise. So for any distribution x and z, as long as x and z are independent, then we have the following inequality, that 2 raised to 2 times h of y is greater than or equal to 2 raised to 2 times h of x plus 2 raised to 2 times h of z. So we'll discuss this in more detail later as to why this is called the entropy power inequality, and where power comes from. And we'll see that this is closely related to this gives you something nice when this is a Gaussian channel. Okay, but anyway, so the connection to this particular problem to the BSC is the following. So in some sense, the BSC is also kind of an additive channel, but the addition is not over the reals, but in fact the addition is over the binary field. So the BSC can be represented as this additive channel where the addition is not your addition over the reals or over the integers, but it is basically the binary XOR. So the BSCP can be represented as the XOR of the input with a Bernoulli P random variable. So y is equal to x XOR z, where z is Bernoulli P. Okay, so there's a large body of work on trying to understand lower bounds on the entropy of the output of such additive channels. And Mrs. Gerber's lemma is one example. The entropy power inequality is another example of such an inequality. All right, but maybe before we actually try to prove this, let's look at an example to understand this better. Okay, so let's take a random variable u, which is, let's say, Bernoulli. So pu of 0 is equal to 0.2 and pu of 1 equal to 0.8. So u takes values either 0 or 1. The probability that u is 0 is 0.2. The probability that u is 1 is 0.8. Okay, and suppose that we generate an x according to the following distribution. So given that u is 0, x is Bernoulli 0.7. Given that u is equal to 1, x is Bernoulli 0.4. So u equal to 0 implies that x is Bernoulli 0.7, and if u equal to 1, then x is Bernoulli 0.4. Okay, so basically I generate a random bit u. I get either 0 or 1. If I get a 0, then I generate x according to Bernoulli 0.7. If I get u equal to 1, then I generate x according to Bernoulli 0.4. And given that I have this x, I pass this through the BSC channel, the binary symmetric channel with crossover probability 0.3. Okay, so this completely specifies the system, right? So first, what is py given you? Let's calculate these probabilities. What are the conditional probabilities of y given u? Right. So what is the probability of that y equal to 0 given that u equal to 0? Yes, so what is P of y given u of 0 given 0?
Sir, it's 0.2 into 0.3.
How did you get 0.2 into 0.3?
So P of 0 equal to 0.2, right?
So from
Pu of 0 is equal to 0.2, yes, but look at what I'm asking for. So it is Py given u of 0 given 0. Right?
so we can use Bayes theorem and things means P y of y and u both are 0 and y
But
P
you
of y.
don't have to do something that complicated, right? Then you need to first compute P of y. But this is much simpler, right? So you want what is the probability that y equal to 0 given u equal to 0? So just so look at what is happening, right? So you're generating a u, right? So it can be either 1 or 0. From this, you are first generating x, which can be 1 or 0, and conditioned on x, you are generating y, which can be either 1 or 0. So given that u is 1, so you know what these conditional probabilities are. You know what is p of x given u, right? So p of so this is 0.4. The probability that x is 0 given u equal to 0 is 0.3. The probability that x is 1 given that u is 0 is 0.7, and probability that x is 0 given that u is 1 is 0.6. Right? So this part is given to us. We know that pu of 1 is 0.2. Pu of 0 is 0.8. Right? And we also know what Py given x is. It's given by this, right? So this is 0.7, 0.7, 0.3, 0.3. Right? And what do we want to find? We want to find the conditional probability of y given u equal to 0 and u equal to 1. Right? So what all cases are there? So you want y equal to 0 given u equal to 0. Right? And this can happen in two ways. Either u equal to 0, x equal to 1 and y equal to 0, or u equal to 0, x equal to 0 and y equal to 0. Right? So this is p yx given u of 0, 0 given 0 plus pyx given u of 0, 1 given 0, right?
So just before
Okay.
proceeding, PU of 0 is 0.2 we have taken in the top, but here in the diagram we have
Oh, okay, sorry.
yes,
P of 1 is 0.8
0.8.
and this is 0.2. Thanks for clarifying that. Okay, so yes.
Sir, can we convert this equivalent channel into another BSC directly from U to Y?
So think about it carefully. It's not a BSC because after all, this U to X channel is not a BSC. Right? It is not symmetric
Yeah, yes, sir.
because 0 to 1 probability is not the same as 1 to 0 probability. Right? And I may have 0, 1, 0 given 1 is 0.6. 1 given 0 is 0.7. Okay, yeah. Yeah, it's not symmetric. It's a binary asymmetric channel. Right? So the effective channel from U to Y will also be asymmetric. But yeah, you can definitely draw a diagram like this with the crossover probabilities, and that's what we are trying to compute now, right? So this is Py given X of 0 given 0 times Py given, sorry, X given U of 0 given 0 plus Py given X of 0 given 1 times Py given X of 1 given 0.
0.7 into 0.3 plus 0.7 into 0.4.
Sorry, I didn't hear what you said. There seemed to be a lot of disturbance. Can you please repeat?
Yeah, what I'm saying is this will be 0.42. So the total thing will be 0.42.
This will be 4.42. So let's write down the steps. So this will be 0.3 into 0.7,
7.
0.7 plus 0.7 into 0.3, and that you say, yeah, this will be 0.42. Okay, that's fine. So what about Py given U of 1 given 0? Probability that y equal to 1 given that u equal to 0. Right? So probability that y equal to 1 given that u equal to 0. So this can again happen in two ways, when x equal to 1 or x equal to 0 or x equal to 1. So that will be 0.3 into 0.3 plus 0.7 into 0.7. Yes, so what will this be equal to? Anyone?
Point five.
So are these calculations clear? Is it clear how we are getting this?
Yes, sir.
Okay. So now what about P of y given u, probability that y equal to 0 given that u equal to 1? What is this equal to? Any of the others? So Chandramurthy says, so let's do the calculation step by step. So 0 given 1, 0 given 1. So it will be 0.4 into 0.3 plus 0.6 into 0.7. 3 plus 0.6 into 0.7. Right? So what is that equal to?
Point five.
0.54.
0.54. Right? So what about Py given u of 1 given 1? So it is u equal to 1 to y equal to 1. So it will be this into this plus this into this, correct?
So this we can just write 1 minus 0.54.
Sorry, I didn't hear what you said.
What I'm saying is this can be written as 1 minus Py
Correct.
that is
Correct.
0 1.
Sure,
1
yes.
minus 0.54.
Yeah, so you can calculate it directly, or you can also say that this is simply equal to P of Py given U of 0 given 1. Right, so what is that equal to? Point
0.43.
Okay, so uh, sorry, yeah,
4 6.
or 6. Okay, so now we know what are the conditional probabilities of y given u, and we also know what are the conditional probabilities of x given u. Correct? So let's compute the entropies of x given u and the entropy of y given u. Okay. Uh, so what is the entropy of x given u? So this is summation over all x, summation over all u, p of x. Let's write this. Yeah. X u of x comma u log 1 over px given u of x given u. But I want to write everything in this special way, which will make it a little more convenient for us. So I'll sum over u, sum over our x. So I'll write this as p of x comma u as p of u times p of x given u. X given u of x given u times log of 1 over px given u of x given u. And the reason why I'm writing it in this way is because if you look at this term, this is basically the entropy of x given that u equal to little u. Correct? So in general, I can write any h of x given u as summation over all u pu of u times h of x given u equal to little u. And in this case, it's much easier. So this just, you know that when u equal to 0, x is Bernoulli 0.7. When u equal to 1, x is Bernoulli 0.4. Right? So this is, and you can take values either 0 or 1. So the probability that u equal to 0 is 0.2. So it is 0.2 into the binary entropy of 0.7 plus 0.8 into the binary entropy of 0.4. Correct?
Sir, last step was, can you repeat please?
Sorry?
Binary entropy of 0.7 and binary entropy of 0.4. We are taking from previous channel, this model.
So correct. So
Yeah.
so we're using this, right? We're using px given u, correct?
Yes, sir, got it.
So basically it is h of x given u equal to 0. So it is probability of u equal to 0 times h of x given u equal to 0 plus probability that u equal to 1 times h of x given u equal to 1.
Yes, sir.
Right? So what is this equal to?
Nine 9.52.
Yep, so it will be around, yeah, I think, I guess 0.952, right?
Yes.
So it's around point, I think 953 to be more exact. Yeah, so what is
Yes.
0.952, 0.953, something like that. Okay, fine. So now let's look at h of y given u. Okay, so what is that equal to? So now we have p of y given u of 0 given 0, 1 given 0, and so on. Right, so it will be 0.2 into h of y given u equal to u. So given 0, it is either 0.42 or 0.58. 0.42 plus 0.8 into H2 of 0.54.
Not 0.996.
Yeah, so I think it's 0.9925 is what I'm getting, but something around 0.99. 993 something. Okay. Yeah, so there may be some precision kind of thing, but whatever, it's roughly 0.99, whereas h of x given u is roughly 0.95. Okay, so let's see. So this, how would this compare if you try to plug in into this over here? So we know exactly what h of y given u is. We know exactly what h of x given u is. Are the two the same or are they different? Right. So first we need to find h inverse of h of x given u. Okay, and that is okay. So it turns out to be around 0.37. The value of yeah, so the value of h inverse. Let me share my screen. So basically what I've done here is that I've written a function to compute the entropy and to compute the binary entropy of P over here. And I know what h of x given u is. H of x given u is 0.953. I want to find out what h of, so hx given u is 0.953. Okay, and I want to find h inverse of x given u. Okay, so this, I can't find it exactly because I don't have a closed form expression. But what I can do is find the one which is closest to it. So take the absolute value of x given u minus. Right? So you search for that which is closest to h of x given u. Find that p. Right? So this gives me a particular location. So it should have been p of this. And it turns out to be around 0.37. So the binary entropy of 0.37 is 0.9506, and the binary entropy of 0.38 is 0.958. So it's somewhere in between. Fine, that's good enough for us. So 0.37 is h inverse of x given u. So let's compute h. So what we want is h inverse of x, h inverse of h of x given u star p star p, right? Or in this case, our p was 0.8. Right? So this is what we have to compute. So it is binary entropy of H inverse X given U times 0.2 plus 0.8 into 1 minus H inverse X given U. Right, and we get something, it's 0.982. So if I go back to my notes here, right, so h of x given u is 0.953, h of y given u is 0.993, h inverse of h of x given u, this is roughly 0.37, and h of h inverse of this star p, this turns out to be 0.98 something, 0.982. Right. So this is less than or equal to, this is obviously strictly less than h of y given u. Alright. So in general, it's hard to get an exact value, a closed form expression for h of y given u if all you know is only h of x given u. If you don't know the distribution, then it's difficult to get the exact value of h of y given u. But this is a decent enough bound. All right. We'll next discuss the proof of this lemma. But before that, are there any questions? So this was just a numerical example where we computed each of those terms in Mrs. Gerber's lemma. And we basically just verified that at least for this example, Mrs. Gerber's lemma is true. And how much the difference between h of y given u and the right-hand side is. So it's pretty small. Okay, so in your homework, I gave one particular question, and that is to prove the convexity of a certain function. So if you look at the function f of u equal to h2 of h2 inverse of v star p, this is a convex function of v. Okay, so irrespective of what p you take, so note that this is a function of v and p. So for any p between 0 and a half, this function is convex in v. Okay, and basically Mrs. Gerber's lemma is a direct consequence of the convexity of this function. All right. So anyway, this is a homework problem, so I will not solve it. I think there are enough hints to be able to solve it. Basically, you just have to find the second derivatives of various terms and use some nice convexity arguments of those. But let us see how to use this to prove Mrs. Gerber's lemma. So let's recall what we want to show. We want to show that h of y given u is greater than or equal to h2 of h2 inverse of h of x given u star Okay, so let's try to think about each of these terms, right? So given any, so if you look at the following function of x, okay, look at x star p. What kind of a function is this? In x, as a function of x for a fixed p?
Linear.
Exactly, it's a linear function. So this particular term is fine. But what about h inverse? So ultimately, we are interested in this as a function of h of x given u, right? So what about h inverse of something? Is it a convex function or
Non-linear, I think.
it is a non-linear function? But is it convex? Is it concave? So note that h2 of, so the binary entropy is a concave function, right? So what about the inverse? What will the inverse look like?
Convex.
Exactly, just be a convex function, right? So if this is what the function is, then its inverse is basically the same obtained by sort of flipping it around, right? So this would be h2 of alpha. So basically, if this is whatever v, then this is, sorry, this is v, then this is h2 inverse of v. Correct? So this is going to be a convex function, but the binary entropy is a concave function. So it's a concave function of a convex function, right? So it's not trivial to show this result. It requires some thought. But again, in the homework exercise, you will see that this is a convex function. Okay. So now we want to show this particular statement. So and this looks like we already have what we want. So what is h of x given u equal to? So let's look at the RHS. All right. So this is h2 of h2 inverse of h of x given u. So I can write this as summation over all u, pu of u, h2 of, h of x given u equal to u star p. Okay. So recall that I defined this as f of u. All right. So this is my f of u. So this is essentially equal to f of summation over all u, pu of u, h of x given u equal to u. Right. So this is basically a convex combination of h of x given u equal to u. Correct? And we know that f is a convex function. So what can you say? So I want to write this in terms of a convex combination of f of h of x given u equal to u. So is this greater than or equal to? Is it less than or equal to?
Less than or equal to.
It's less than or equal to. All right. So let's go a little bit more slowly. So we have this function. right? It's a complicated looking function, but all we're interested in this argument, right? So h of x given u can be written as summation over all u, p of u times h of x given u equal to little u. Right? And this, no matter what function this over here is, no matter what function this is, all we care about is that this is a convex function, right? And this is a convex combination of h of x given u equal to little u. Okay, so this is as we wanted. Okay, so we have we've arrived at this particular term. So just using the property that f is convex, we get this. Okay, but let's examine what f of h of x given u equal to little u is. Right? So this is equal to h2 of h2 inverse of h of x given u equal to little u star p. All right. So if you fix a particular capital U, for a fixed capital U, x is going to be some Bernoulli QU. For x, for u equal to little u, x is going to be some Bernoulli QU. So I'm just denoting this as a function of u, right? So now what can you say about y? So y is going to be Bernoulli QU star p. Correct. And so what is the entropy of y given u equal to little u? So what is this going to be equal to? This is just h of QU star p. So QU into 1 minus p plus 1 minus QU into p. But this is essentially h of h inverse of u equal to u star p. Right, which is just f of x given u equal to little u. All right. So h of y given u equal to little u is the same as f of h of x given u equal to little u. Now what happens if we plug this back in here? So the RHS is less than or equal to summation u over all possible u, pu of u, h of y given u equal to little u. All right, which is what? This is just h of y given u.
Yes.
All right, so this is h of x given u star p. So this is less than or equal to h of y given u. Okay. So this is a neat argument just using properties of convexity, right? So in doing this, we only use two things. One is, of course, that f is a convex function, and two, exactly what h of x given u is. You can write h of x given u as a convex combination of h of x given u equal to some specific little u, and also you can write h of y given u as a convex combination of h of y given u equal to little u. All right. So go through this once again. I mean, it may seem complicated, but you can only get it by trying to work it out yourself. But conceptually, there is nothing deep going on over here. So it's just a simple sequence of inequalities using properties of convexity and the exact definition of conditional entropy. All right. And a lot of it is, so all of this is basically, these are all geometric kind of ideas, right? You look at convex functions and then you think what must happen. And these are basically all the properties that we're going to use to prove this particular result. Any questions? So this particular proof is not really available in the textbook. So you can just look at my notes, as well as you'll have to prove this particular result on your own, right? And use the hints which are there in the homework problem. Right? You prove that this particular function is convex. You look at the second derivative of this with respect to, basically the goal is to find the second derivative of this and show that it is greater than or equal to 0 for all p. All right. Okay, so any questions? Okay, so if not, then we meet in the next class, where we'll continue this discussion and also start discussing the more general version for continuous random variables, which is the entropy power inequality.